Hello guys, in physics we are going to chapter 12. Chapter 12 is about rotational energy, rotational momentum, rotational dynamics, that sort of thing. And they're very analogous to everything you've already learned. So just like, rotational kinematics were very analogous to your normal linear kinematics, it's going to be kind of the same situation here. Let me show you a couple of things that I mean here. Watch me work my fancy surface pen. So you know how kinetic energy, okay, my surface pen, what is it doing? There we go. You know how kinetic energy was equal to 1/2 mv squared? Well, rotational kinetic energy, which I'm not sure the name of it, so I'm just going to say rotational kinetic energy. There's probably a letter for it, but I can't remember it. Is 1/2, and instead of mass, there's something called the moment of inertia, which is the rotational equivalent to mass. So just like mass is kind of an object's inherent characteristic that makes it resistant to change its motion, that's what the moment of inertia is for rotational stuff. So in its letter is I, and then instead of a v squared, it's omega squared, which, if you'll remember, that is angular velocity. Force, F equals ma. That's what makes an object accelerate in a linear direction. Well, what makes an object accelerate in a rotational direction is torque. The symbol for torque is this Greek letter tau. It is equal to force times the distance, or radius. So you know how work is equal to force times distance, but that's if you push in that direction with a force and it goes this far. That's the force, that's the distance, and they're in parallel directions. Torque, they're not in parallel directions, they are in exactly perpendicular directions. So your force may be this way, and your distance may be this way. So imagine, like, here's a screw. You're trying to unscrew, and it's really hard to unscrew. What makes it easier to unscrew is if you have a longer wrench, right? So the longer the wrench is, the more torque you get. It's the force, not times the parallel distance, but times the perpendicular distance. The distance that the force is away from some central turning point. All right, so that's what that R is. R is that distance there, that radius from the center of rotation. Torque is also equal, just like so torque is the rotational equivalent of force. So just like force equals ma for linear stuff, torque equals, remember what I is analogous to, is equal to I. This is something called moment of inertia. And then instead of an A, we have, what do you think? An alpha, angular acceleration. Now, let me relate M and I a little bit more. Basically, I is equal to, it's M squared R squared. So it's kind of strange to think about, but let's say you have this object and it has some center of mass right in here somewhere. Well, each one of these little particles in here has some minute mass, and it's some distance away from that center of mass. If you add all of them up, if you add all these little particles' moments of inertia, it gives you the overall moment of inertia for that, whatever that object is. So that is how we figure out the moment of inertia. And so each one of these things has an M and it has an R. Each one of these particles does. And so that's how we figure out the moment of inertia. Another analogous thing we have, you know how we have angular momentum, which I believe is, we have linear momentum, which is P. Remember what that's equal to? Just had a test over it, I think. mv, mass times velocity. That's kind of an object's tendency to remain in motion along its line of direction. Well, there's also an angular momentum. I'm trying to think of the letter for it. I can't remember it. So angular momentum or rotational momentum, I'm going to call it, I don't know, RP for now. We'll change that letter when we figure out what it is. But it is equal to, what do you think? You can probably guess it. I omega. All right, let's get into our PowerPoint. Rotation of a rigid body. What is a rigid body? An object whose size and shape don't change as it moves is called a rigid body. So if the thing changes its shape as it rotates, this does not apply. So if something breaks when you're swinging it really fast, then the rotational physics that we're studying doesn't work. You have to use some other model. But a couple of examples of this is rotation about an axle. So like this wheel, imagine it rotating about that center point, but also rolling without slipping. So imagine now this being the center point and this thing going around it, which is kind of what rolling without slipping is. So that it kind of has two axes around which it is rotating as it moves linearly and rotationally. So we'll think more about that later. What is torque? Torque is the tendency or ability of a force to rotate an object about a pivot point. You'll learn that torque depends on both the force and where the force is applied, as we said. A longer wrench provides a larger torque. So if you got a heavy door, if you push on the door really close to the hinge, it's going to be a lot harder to push that door open or pull than if you push or pull much farther away from the hinge, because that gives you greater torque. It gives you a longer radius, which increases the torque. What does torque do? Torque is to rotation what force is to linear motion. Torque, tau, causes an object to have angular acceleration. So Newton's second law, you can write it as tau equals I alpha, or you can rewrite it, if you rearrange it, as alpha equals tau over I. Much of rotational dynamics will look familiar because it is analogous to linear dynamics. What is angular momentum? Angular momentum is to rotation what momentum is to linear motion. We've kind of already talked about that. It has, so here's the letter for it. It is L. So I forgot the letter. So P is linear momentum, and L is angular momentum. So let me go back to the thing I had before. So instead of rotational momentum, let me write the correct letter here. It is L. All right. Why is rigid body motion so important? The world is full of rotating objects. Windmill turbines, gyroscopes used in navigation, the wheels on your bicycle or car. Scientists investigate rotating molecules and rotating galaxies, from the itty-bitty to the grandioso. No understanding of motion is complete without understanding rotational motion. And this chapter will develop the tools you need. We'll also expand our understanding of equilibrium by exploring the conditions under which objects don't rotate. So that's a really important thing for an engineer, for an architect. You don't want things to move. So that's a class you're going to take called statics. And the whole key to statics is that the sum of the forces equals 0 and the sum of the torques equals 0. That's what you want to be the case when you're designing a bridge or a building or something like that. Chapter 12, reading questions. Chapter 12, reading questions. Let's see here. All right, when floating in space with no external forces acting on it, an object tends to rotate about its what? What would you think? B, center of mass. All right. A rotating object has some rotational kinetic energy. If its angular speed is doubled, but nothing else changes, the rotational kinetic energy does what? Okay, something I need to tell you that I think I told you wrong before was this part. This was wrong. It's not m squared r squared. I is just m r squared. So the m is not squared, just the r squared. I is m r squared. All right, back to the question here. So that's I need to erase that part. Or maybe I can just erase it with this part. Yes, I can. All right, so if I is mr squared, a single particle has a mass m and it is a distance r away from the origin, then the moment of inertia for this particle about the origin is what? Should be just E, and it is. All right, when discussing torque, the line of action is what? The line connecting the pivot with the point where the force acts. That sounds like a pretty good option. The line along which the force acts. That is, I don't think that could be it. B. So if it's this is the pivot point, and here's the lever arm, and here's the force, then choice A would be this lever arm, whereas choice B would mean it would be this line along which the force acts. I think it's this, actually. I think it's B. So like if you were maybe applying a force like this, then your line of action would be this, and you would then have to extend the lever arm to there for it to actually cross the line of action. So I think it's B. Let me read C, D, and E. The line that passes through the center of mass, the line along which the motion occurs, nope. The axis around which the object rotates, nope. So I think it's B, but A and C are possible. Yeah, it's B. That's good. All right, a new way of multiplying two vectors is introduced in this chapter. What is it called? It is called the cross product. So, yeah, let me make sure. Yep. So the dot product was when it was like F vector dot D vector, and that's for work. That's when the force and the distance are parallel to each other, force acting along a distance. But the cross product, F vector cross the D or R vector, that's equal to torque, tau vector. So I think this one is basically turns into the force magnitude times the D magnitude times the cosine of the angle between them. Whereas this one, I think, turns into the same thing, except it's not cosine, but sine. All right. Let me go back. I want to talk to you more about this. If this is the radius, here's the axis of rotation. Something's rotating along this axis. And we do a force like this. Then this is R and this is F. Then this is a 90-degree angle between them. And sine of 90 is 1. So that means it's just, if it's perpendicular already, then it's just F times R. But if the force is acting at an angle not 90 degrees, here's theta. then basically what we need to do, that's not drawn very well, but basically what we need to do is we need to figure out the component of the force. We draw this angle here, or we can even draw it like this, draw this triangle here. Figure out the component of force that is perpendicular. I could change colors, couldn't I? And I think I could change colors. Draw. Yeah, look at that. Figure out, nope. Give me red. Come on now. There we go. Look at my new color. Figure out the component of the force that is perpendicular to the radius. So that would certainly be the sine of theta. It would be F times sine of theta. That would give me, because that's the opposite side from theta, that would give me this right here, the component of force that is perpendicular. So I multiply that times that full length R, and that will give me the correct torque. All right, moving on. Moment of inertia is what? The rotational equivalent of mass. I like that answer. Yep. A rigid body is in equilibrium if the net force equals 0, if the net torque equals 0, neither, either, or both. Both. Choice E. All right. We have these kinds of motion. Let me get my... Okay. We have translational motion where something is just moving, but it's not rotating. We have rotational motion, and then we have both happening at the same time. This thing is moving, it's translating, but it's also rotating as it translates. All right. So every point on this wheel rotates with the same, this is kind of a review, with the same angular velocity, omega. So it doesn't matter where the point is, they have the same angular velocity, the same angular acceleration, the same change in angular position, and so on. But the linear distance, the linear velocity, the linear acceleration is not the same. And remember how those are related is like, so if you have omega multiplied by r and you get the linear velocity. If you have alpha multiplied by r, you get the linear acceleration. If you have theta, that's the angular position or the change times r, that'll give you the distance or the circumference or whatever. Remember, omega is d theta dt, alpha is d omega dt, and so on and so forth. All points have a tangential velocity and a centripetal acceleration. So the acceleration always points toward the center of the circle. Tangential acceleration points toward along the line of motion, so perpendicular to the radius. They have tangential acceleration if the wheel has an angular acceleration only. So if it's uniform circular motion, there is no tangential acceleration if it's uniform, and that means it's going at a constant angular velocity. Rotational kinematics, you know this like the back of your hand. A equals A. Well, in this case, alpha equals alpha, and then anti-derive from there. So omega F equals alpha T plus omega I, and like YF or theta F equals 1/2 alpha T squared plus omega IT plus theta initial. And then this one that's always kind of, it's not derivable, but it does come in handy, where it's like VF squared equals VI squared plus 2A delta S, but in this case, omegas and alphas and thetas. All right. Remember that counterclockwise is positive in rotation and clockwise is negative. So what if we have going this way and it's speeding up counterclockwise? If that's the case, then omega is positive and alpha is positive. What if it's going this way, speeding up counterclockwise? Then omega is negative and alpha is negative. what if it's going clockwise and slowing down? Then omega is negative, but alpha would be going the other way. Alpha would be positive. What if it's going counterclockwise and slowing down? Then omega would be positive, but alpha would be negative. Quick check, 2 coins rotate on a turntable. Coin B is twice as far from the axis as coin A, so the angular velocity of the two compares how? They are equal. Now their tangential velocity or linear velocity, B would be, since it's omega r, B would be twice as much of a linear velocity. Fan blade is speeding up. What are the signs of omega and alpha? Speeding up in the clockwise direction. So both of them would be negative. All right. An object that is unconstrained when it's rotating will, if you just throw something, it's going to rotate about its center of mass. So the center of mass, this point right here, remains quote unquote motionless, while every other point in the object undergoes circular motion around it. So if you think about this, this point right here is not rotating in a circle. Think of this as an infinitesimally small point. All right, consider an object made of particles. The center of mass, imagine this object right here. The center of mass is kind of like calculating a GPA. All right, so the more mass and the farther away it is from, think of the mass as like the grade that you make on an assignment, and think about the distance away from the center of mass. Think about that as how much that assignment counts. Or you could think about it vice versa from what I just said. But then you divide all of that by the total mass. All right. So that's the same thing that's written here. The sum of all those mass times positions, and then times 1 over the total mass. And you do that for the horizontal direction and for the vertical direction to get an overall location, an overall point, ordered pair for the center of mass of an object. All right, here's a good example. This barbell is unbalanced. It's got a 2 kilogram mass on one end and a 500 gram mass on the other end, and it's connected by a massless, quote unquote, massless 50 centimeter long rod. So what you do, use that formula from earlier. All right, notice how they have put the 2 kilogram weight. They made that be at 0, so that's going to be convenient. And they made the 0.5 kilogram weight, 500 grams, 0.5 kilograms, be down here, and it is, since it's a 50 centimeter long rod, then it's 0.5 meters away from 0. So we're going to apply this this formula, the center of mass, and we're not going to have a y coordinate because this is just a kind of a flat situation. It's just a flat rod with weights on the ends, so it's not like a blob thing that you're going to have to do vertical and horizontal type of stuff. So the center mass is x1, sorry, it's m1 x1 plus m2 x2 plus m3 x3 and so on, all over the total mass. So in this case, it is 2 kilograms times 0, because the x coordinate of that is 0 since we defined our origin there. That's why that's convenient. Plus 0.5 times, that's 0.5 kilograms times the 0.5 meters that it is from the origin plus M3 would be the rod itself, and we could treat the rod as if all the mass is in the center of the rod, but it said that the rod's massless, so I actually don't have to worry about that. So I don't have to worry about anything else. So that's gone, and that's gone, and so all that's over the total mass, which is 2 plus 0.5. So that's over, and nothing, so plus 2.5. I'm still here. Yes, I'm still here.
Hey, John, can you still hear? Okay.
So that gives us that's 0.25 over 2.5. Let's see, what is that? That's going to be 0.1. So 0.1 meters or 10 centimeters. So the center of mass is 10 centimeters or 0.1 meters away from where what we called 0, which was away from the 2 kilogram mass. So if this is a 50 centimeter long rod, it's a fifth of the way down the rod, or 20% down the rod is what they say here. All right. Yeah, so what is it? What else does it ask? What is the speed of each ball if they rotate about the center of mass at 40 RPM? 40 RPM. They rotate about the center of mass. Okay, so the speed is 40 RPM. I need to get that to be in not revolutions per minute, but I needed to get it in radians per second to get it. Then from there, get it in meters per second. So that's revolutions per minute. So 1 revolution is 2 pi radians, and 1 minute is 60 seconds. That'll give me radians per second. So that gives me, let's see here. My calculator tells me that is 4.2 radians per second. So that's omega. So then omega r is the velocity. So 4.2 times 0.1. This is for the 2 kilogram ball. Which is 0.1 meters away from the center of mass. So its velocity is going to be 4.2 times 0.1. That's going to be 0.42. 0.42 meters per second. And then for this guy, the 0.5 kilogram, is going to be 4.2 times 0.4, because that's how far it is away from the center mass, which is the center point around which everything is revolving. So that's times 0.4. So that's going to be 1.68 meters per second. All right, let's get back to it. Let's see if we got it right. Yep, got it right. All right, I am going to pause it right here, and maybe I'll just call this part 1 and do the rest in a separate video.